Hello everyone and welcome to this video. Today we're discussing the phenomenon of electromagnetic waves. Now to give you some context, we have actually learned some phenomena that preceded the prediction of electromagnetic waves. We saw, for example, that a stationary charge produces an electric field in the region surrounding it. We also learned that moving currents produce magnetic fields in the region surrounding them. And this was discovered, of course, by Oersted experiments. So let's take a moment here and realize what we have learned so far. We know that electric charges produce electric fields and moving charges, that is electric currents, produce magnetic fields. But then came along Faraday and did something phenomenal. He went ahead and showed that a changing magnetic field produces an electric field. And this was amazing because this meant that changing one of these two fields produced the other. And then, of course, the logical next question was, can a changing electric field produce a magnetic field? And for a while, no one knew if this was possible. But soon enough, we got the answer, and this answer was provided by Clerk Maxwell. Maxwell stated that the magnetic field can indeed be produced by a changing electric field. And he actually came to this conclusion when he was trying to do an experiment with a capacitor. He was trying to find the magnetic field at a point inside and outside the capacitor using Ampere's circuit law. When he was doing this, he was using a current that was changing in time, which meant that he was using a changing electric field. And when he tried to use Ampere's law, he saw that the answers weren't consistent. And what does that mean? We'll see how these answers were not consistent. But it is this inconsistency that made Maxwell come to the conclusion that some piece of the puzzle is missing. And he put in this piece of puzzle by saying that a magnetic field is produced by a changing electric field. This missing piece of the puzzle was actually the concept of displacement current. This concept actually helped us find the missing piece of Ampere's law, and then Maxwell gave the four legendary equations, Maxwell's equations, all of which led to the prediction of the electromagnetic waves, which we will be studying today. So let's look at the experiment which led Maxwell to conclude that changing electric fields produce magnetic fields, and through which he conceptualized displacement current. Now in this experiment, like I said, he was working with a capacitor. Now we know that whenever a capacitor is connected to a battery, the capacitor starts charging, which means that conduction current starts flowing through its wires. As the conduction current is flowing, the capacitor begins to charge, and as it begins to store this charge, the conduction current reduces. So as the charge on the capacitor increases, the conduction current in the wire decreases, and at the point where the capacitor is fully charged, we know that the conduction current stops flowing in the wire. However, what is now created is an electric field between the plates of the capacitor, as you can see for yourself. This electric field is created because of the stored charges on the plates of the capacitor. Now, during the charging of the capacitor, there is no conduction current between the plates of the capacitor. In fact, even when the capacitor is fully charged, there is no conduction current between its plates. In fact, what exists is an electric field. And because the current is changing while the capacitor is charging, this electric flux between the plates is also changing, and therefore the field that exists between the capacitor plates is also changing. Let us see at some instant what is happening while the capacitor is charging. So during the time of charging, let us look at one instant of time when the conduction current is denoted by IC. At this point, the conduction current is IC and has some value. Now, because of conduction current, there will obviously be a magnetic field created in the region around the wire. We already know this, that currents produce magnetic fields. And what Maxwell wanted to do was try to find out the magnetic field at some point, let's say R, outside this wire. This point R lies on a loop of radius small r. To find out the magnetic field at point R, what Maxwell did was use Ampere's circuit law. And to use Ampere's law, we know that we require an Amperian loop. So as you can see, we have considered a plain circular loop C1 of radius r, which is our Amperian loop. The plane of this loop is perpendicular to the direction of the current carrying wire. Why is this useful? This is useful because, as we have learned before, when this happens, we can use the reduced form of Ampere's circuit law. You see, in this case, the magnitude of the magnetic field is same at all points on the loop and is acting tangentially along the circumference of the loop. And because of this, we can use the reduced form of Ampere's circuital law. We know that in Ampere's circuital law, on one side we have the magnetic flux integral. This integral simply reduces from B dot dl to B dl cos 0 because the magnetic field and the current element are tangential and therefore the angle between them is simply 0, and therefore this reduces to simply the magnitude of B multiplied by the length of the Amperian loop, that is B into 2 pi r. This is equal to mu naught times the current enclosed, and the current enclosed by the Amperian loop is nothing but the conduction current IC, and therefore we get that B 2 pi r is equal to mu naught IC, or B is equal to mu naught IC upon 2 pi r. This gives us the value for the magnetic field at the point r outside the capacitor. Now what Maxwell tried to do is try to find this magnetic field at the same point using a different surface. Instead of using the surface which is on the outside, we consider a different surface which has the same boundary as the loop C1. As you can see, this surface is sort of like a tiffin box or a pot without a lid. What is so special about this surface? Well, what happens is that you can see that this surface is passing between the plates of the capacitor. And what lies between the plates of the capacitor? Just the electric flux. There is no conduction current between the plates of the capacitor, and hence if you take a careful look at this surface, there is no conduction current passing through this surface, and hence the enclosed current for this surface is 0. And if there is no enclosed current, if I apply Ampere's circuital law, I will find that the magnetic field comes out to be 0. When I used one surface, I got some value of the magnetic field at point r, but now when I am using a different surface, at the same point I am getting a different value of the magnetic field, and this is obviously wrong. So Maxwell said that Ampere's circuital law is logically inconsistent, that is, something is missing, and he set out to fix it. How do you fix this law? Well, you have to do something such that you get the same magnetic field whatever surface you might choose. And to get this same magnetic field, he had to introduce the concept of the displacement current. Let's take a step back and think what he was thinking when he thought of the displacement current. Well, you see, the magnetic field at point r was found using the first surface by using some enclosed current which was the conduction current. In this case, that is in our second case, when we had the tiffin box surface, we had no enclosed current, and therefore the right hand side of Ampere's law just became 0. So obviously there is some problem here. The right hand side should not go to 0. Even though there is no conduction current, there must be some kind of current that it is enclosing. And this some kind of current must actually be because of the changing electric flux. And this changing electric flux produced this current which Maxwell called as the displacement current. And if there is a current in the region between the capacitors, then definitely there is a magnetic field in the region between the capacitors. And thus Maxwell showed that a changing electric field, that is the one in between the capacitors, produced a current, which is the displacement current. And if there is a current, there is definitely a magnetic field. So let's see how he postulated the displacement current. He said that we know already that between the plates of a capacitor lies the electric field given by the formula E is equal to Q upon epsilon naught A, where Q of course is the charge on the plates of the capacitor and A is the area of cross section of these plates. Once you have E, it is easy to find the electric flux between the plates. We know that the field is perpendicular to the surface S, and once we know that, we can calculate the electric flux very easily, because flux is nothing but E dot A, but because they are perpendicular, it comes out to be EA simply. And now we can use the formula for E into this equation for flux, and we get that phi is equal to Q upon epsilon naught A into A. The A's cancel, and this gives me that the electric flux is simply Q upon epsilon naught. Once I have this electric flux, I have to find some way in which I can show that a changing electric flux produces some kind of current. And if I want to find out what a changing electric flux does, then I have to find d phi by dt. So when I do d phi by dt, I see that this leads to ddt of q upon epsilon naught, but epsilon naught is a constant, so it goes out, and therefore I get d phi by dt is equal to 1 upon epsilon naught dq by dt. I take dq by dt on one side alone, and I take epsilon naught to the other side, and this gives me dq by dt is equal to epsilon naught d phi by dt, and we all know what dq by dt is. It is a rate of change of charge, which is nothing but a current. So as you can see, voila, we can see that a change in the electric flux is producing a term which is a current, and this is the current that is passing through the surface S. Even though there is no conduction current, there is a current, and this current is the displacement current, which is related to the changing electric field. We call it ID, that is Maxwell's displacement current. And now, once Maxwell proved that there should be some kind of displacement current, he changed Ampere's circuital law to include this displacement current. And therefore, we say the displacement current is that current which comes into play in a region in which the electric field and the electric flux is changing with time. So now we have found the displacement current. It is the missing term of Ampere's law. It's time to add it to Ampere's law. Now we modify Ampere's law as Maxwell did. That is, the right hand side now is not just mu naught IC, but there is also another term, that is ID, where ID is the displacement current. This is the modified form of Ampere's circuital law, and therefore now I can replace ID with the formula we found, and this gives me the final modified version of Ampere's circuital law, where phi E is the electric flux across the loop that you are considering. The most important property that was useful in finding this displacement current is the understanding that the sum of conduction plus displacement current is a continuous term along any closed path. Even though individually IC and ID may have different values, together as a sum, that is IC and ID, are always consistent. That is, they always have the same constant sum. And this was the modified form of Ampere's circuital law. So let's verify this statement. That is, let's verify if the sum of conduction and displacement current is the same across any closed path. So to verify this, we'll have to go back to the setup that we were looking at before. And we already have the equation for the displacement current. That is, it is epsilon naught times the change of electric flux with time. Here I have the same setup as before. We have two capacitor plates, and we say that we're looking at some instant of time during which the capacitor is charging. So while this charging is taking place, we are looking at one instant of time where I say that the current passing, that is the conduction current passing through the wires, is I or IC. Now we consider two separate loops, one C1 placed outside the capacitor and two C2 placed inside the plates of the capacitor. Now what we're going to do is prove that the sum of conduction and displacement current is the same for the outer loop and the inner loop. For the inner loop, that is C2, we can see that there is no conduction current, but there is a displacement current. However, like I said, there is no conduction current between the plates of the capacitor, and hence no IC exists for the loop C2. For the loop C1, on the other hand, there is a conduction current, but there is no change in flux. And because there is no change in flux, there is no displacement current. So let's try to write down what is I plus ID for the outer loop C1. For C1, I plus ID will simply be equal to I plus epsilon naught d phi by dt. But like I said, there is no flux for the outer loop, and therefore there is no change in flux, and therefore I plus ID is simply just I, because there is no displacement current for the outer loop. For C2, on the other hand, we see that the sum I plus ID will be simply equal to ID itself, because there is no conduction current. So here I get that I plus ID is equal to ID, and for ID we write down the formula as we have from formula 1. So I get I plus ID is equal to epsilon naught d phi by dt. So I have found the expression for I plus ID for loop 1 and for loop 2, that is for C1 and C2, and these are the formulae 2 and 3. And what is my goal here? My goal here is to show that I plus ID is the same for loop C1 and for loop C2, because that's what I'm claiming, that the sum will be the same irrespective of the loop you choose. And now if I want to prove that, I have to prove that equations 3 and 2 are equivalent. So to do that, I first recall that the electric field between the plates of the capacitor E is given by Q upon epsilon naught A, and the electric flux is given by Q by epsilon naught, as we have shown earlier in this chapter. Once I have the expression for phi, I can simply take equation 3, that is I plus ID is equal to epsilon naught d phi by dt, and instead of phi, I can replace the expression for phi from equation 4, and that will give me I plus ID is equal to dq by dt, and dq by dt is nothing but I, or the conduction current itself. And thus you can see that the equation 3 just became equation 2. We began from equation 3 and reached equation 2, which proves to us that these two are the same equation. And therefore this proves that we receive the same result whether you look at loop C1 or loop C2. And so we have claimed that the sum I plus ID has the same value on the left and right hand side of the plate P of the parallel plate capacitor. And in general, it means that the sum of displacement and conduction current is a constant across any closed loop and will not change. Hence, we say that I plus ID has the property of continuity. Remember, it is this addition that has the property. Individually, I and ID are not remaining constant. Together, they are constant through any closed path. So finally, from the discussion of displacement current and the continuity of I plus ID, we have reached the conclusion that magnetic field actually has two sources. That is, you can create a magnetic field in two ways. One is by changing the electric current, that is nothing but the conduction current, and the other is by changing the electric flux, which will give rise to the displacement current. So conduction current is a result of moving charges, a displacement current is the result of changing electric flux, and both of them give rise to magnetic fields, and thus we have two sources for magnetic fields. In general, both the conduction and displacement current will be present, giving rise to the total current, and therefore the total current in any medium is the addition of the displacement and the conduction current. In a conducting medium, conduction current will obviously dominate over the displacement current. However, in an insulating medium like the medium between the plates of a capacitor, in such a case the displacement current dominates over the conduction current. It is also important to remember that the displacement current has the same physical effects as the conduction current, and they both give rise to magnetic fields. Once Maxwell had discovered the displacement current, he went on to formulate the legendary Maxwell's equations, and he used these equations to predict the existence of electromagnetic waves. To understand how he reached the conclusion of the electromagnetic waves, let's first summarize what we know about the electric and magnetic fields. We have already seen that electricity and magnetism are definitely related. We look at the source of the electric and magnetic fields, and we already knew that a static electric charge gives rise to an electric field. And this was given to us by Coulomb. That is, he told us what the force between electric charges should be and what is the value of the electric field due to a charge. Similarly, we also knew what is the source of the magnetic field. We found from Oester's experiments that moving currents produce magnetic fields. However, the real interrelation between the electric and magnetic fields came when Faraday first performed his experiment that proved that a changing magnetic field could give rise to a current. And logically then, Maxwell entered the picture and basically proved that a changing electric field could also give rise to a magnetic field, and he did that by proving that a changing electric field gives rise to a displacement current, and all currents are associated with magnetic fields, and thus Maxwell showed that a changing electric field gives rise to a magnetic field. And thus the picture was complete. Electric field could produce a magnetic field, and magnetic field could produce an electric field, and this is what we call the beautiful symmetry of the electromagnetic interaction. Thus we proved that there is symmetry between the electric and magnetic fields, and this made Maxwell think. He said that okay, when the electric field is changing, the magnetic field is created, and when the magnetic field is changing, an electric field is created, which means that they both are always helping each other produce each other. And therefore, he thought that if I had an electric field and I changed it, this would give rise to a magnetic field. But because the electric field, the original electric field is changing, the magnetic field which this electric field is producing is also changing. And therefore, this changing magnetic field will in turn produce another changing electric field, which will in turn produce another changing magnetic field, and so on and so forth. And thus, Maxwell concluded the existence of the electromagnetic wave. That is, electromagnetic waves will exist in a region where electric and magnetic fields were changing with time. So if you have electric and magnetic fields both changing with time, they will help each other out, because the changing magnetic field will help the electric field by adding to it, and the changing electric field will help the magnetic field by adding to it. And thus, he said that electromagnetic wave will be created by changing electric and magnetic fields with time. He mathematically predicted the existence of the electromagnetic wave by using Maxwell's equations. Maxwell's equations, along with the Lorentz force equation, basically explain all of electromagnetic interaction. Let's quickly take a look at what these equations are. The first Maxwell equation is nothing but the Gauss's law in electrostatics. We have already seen this in the chapter on electrostatics. Whenever you want to find the electric field in a case of symmetry, you take a Gaussian surface and you ask what is the electric flux cutting this Gaussian surface. For example, in case of a cylindrical Gaussian surface, we found that only the curved surface is cutting the electric flux. And thus then you apply Gauss's law, in which one side of the equation is the electric flux and the other side has the charge enclosed divided by epsilon naught. And thus the first Maxwell equation is nothing but the Gauss's law of electrostatics, which basically taught us two important things. One is that an electric field can be calculated due to a discrete charge or a certain charge distribution using this Gauss's law, and two, that this law proves the existence of a single isolated charge. And how does it do that? Because if you trap a single charge in a Gaussian surface, you'll see that the flux or the electric field lines coming out of that surface are definitely non-zero, which means that only by looking at the flux on the outside you can tell that there is charge inside the surface. You are able to enclose a single charge in a Gaussian surface and its effect is felt outside by looking at the flux. And this proved that a single charge can be isolated, because you can take it in a Gaussian surface and trap it, and all the flux coming out will only tell you the effect that the electric charge is present inside. Why is this so important? Because on the contrary, Maxwell's equation, that is the second Maxwell's equation, is the Gauss's law in magnetostatics, which is saying that the magnetic flux through any closed surface is zero. And this is important because on one side you have the surface integral of the magnetic field over a closed surface, and when you trap this in a Gaussian surface as before, you'll see that this time the flux is zero, which means the number of lines going inside is equal to the number of lines coming out of the surface. And this is the main conclusion that you draw from Gauss's law in magnetostatics, that the number of magnetic lines of force entering a closed surface is equal to the number of lines leaving it. And this proves that there is no starting or ending point of magnetic field lines of force, and that you can never trap a single pole. Like you cannot just trap a north pole, because if you trap a north pole, then the total flux is going to be zero. The number of lines going inside and coming out is zero, and therefore you can never isolate a pole, and thus this proved that isolated monopoles, magnetic monopoles, do not exist. The third Maxwell's equation talks about Faraday's law of electromagnetic induction. This law came from the experiment that a changing magnetic field produced an electric current, that is, relative motion between a bar magnet and a coil produced current in that coil. If you take a close look at this equation, the one side of this equation has nothing but the EMF. That is, E dot dl is nothing but voltage. So on one side you have the EMF, the induced EMF that we learned in Faraday's experiment. And so one side is the induced EMF, which is found by taking the line integral of the electric field. And this line integral is taken over this curve which encloses the same surface over which you are taking the surface integral on the other side. So basically I'm saying that one hand side of this equation is the EMF and the other side is the rate of change of magnetic flux, because BdS is magnetic flux and ddt of that is the rate of change of magnetic flux. So basically this equation is E is equal to minus d phi by dt, that is induced EMF is rate of change of magnetic flux. The conclusion we drew from the third equation is that we got a definite relationship between a changing magnetic flux and the production of the electric field, and this cemented the relationship between the electric and magnetic fields forever. The fourth Maxwell's equation is the Ampere circuital law, which was modified by Maxwell and is hence also sometimes known as the Ampere-Maxwell law. As you can see, the one side of this equation is nothing but the line integral of B, that is B dl, and the other side is mu naught, and you have I and you have ID as well. So the first term has the conduction current term and the other is the displacement current term, and therefore you can see that from Maxwell's experiment on the capacitor, you added an extra term in Ampere's law, where on one side you had the line integral of the magnetic field around a closed path, and on the other side you had the conduction current and the displacement current terms. So these are the Maxwell's four equations. The fourth equation is significant because it predicts that the magnetic field can be produced not only by a conduction current but also by a displacement current. The last equation, which is vital to electromagnetic interaction, is the Lorentz force equation. Also something we have seen, that is the Lorentz force on a charge in an electric and magnetic field is nothing but the addition of the force on the charge in an electric field plus the force on the charge in a magnetic field, that is F is equal to QE plus V cross B. So the force is equal to the electric force plus the magnetic force, and together all these equations are enough to deal with any electromagnetic interaction. Finally, remember that the equations that we have written down are only for free space, that is when there is no medium. Maxwell predicted the existence of electromagnetic waves by using the fact that a changing electric or magnetic field will produce the other field. And therefore, he concluded that if I have a changing electric and magnetic field in such a way that their vectors are perpendicular to each other, then what will be created is an electromagnetic waves. That is, the changing part of the electric field will give rise to the changing part of the magnetic field, which in turn will give rise to the changing part of the electric field, and so on and so forth. And thus he predicted that there would be an electromagnetic wave, and this electromagnetic wave, when it will propagate into the medium, it will give rise to electromagnetic disturbances. And he said that electromagnetic waves are those in which there is a sinusoidal variation of the electric and magnetic field vectors in such a way that they are at right angles not only to each other but also to the direction of wave propagation. He also predicted that electromagnetic waves would not require any material medium for propagation. This was a very big thing because up until then the only waves that were known were waves like sound waves, which were longitudinal and required a material medium for propagation. We know that sound travels because of vibrations of the material particles. Similarly, the other waves known were, for example, water waves, which were transverse waves, but they were created on the surface of water and also again required a material medium for propagation. Maxwell said that electromagnetic waves do not require any material medium for propagation, and this was a huge thing. In fact, he went one step ahead and even found the speed of these waves in free space, and he said that this speed of the electromagnetic wave would be equal to c 1 upon root mu naught epsilon naught, where mu naught is of course the permeability of free space and epsilon naught is the permittivity of free space. And if these electromagnetic waves are in a material medium, that is, they are not in space, then this equation will change to 1 upon root mu e, where mu is nothing but mu naught mu r, that is, it is the permeability of the medium given by mu naught into relative permeability, and epsilon is epsilon naught into epsilon r, which is permittivity of free space into the relative permeability, and therefore the new equation, which is V is equal to 1 upon root mu naught mu r epsilon naught epsilon r, and therefore I can write V is equal to C upon root mu r epsilon r. So far we have learned that Maxwell not only predicted the existence of electromagnetic waves, he also predicted that they will not require any material medium. He gave a formula to find their speed, and finally, and the most important discovery and prediction from this was that he said that light is an electromagnetic wave, and he actually found the speed of light theoretically using this equation, that is c is equal to 1 upon root mu naught epsilon naught. And that is why the prediction and theoretical considerations of this theory proposed by Maxwell were of great importance, because he could actually find that light is an electromagnetic wave which is transverse in nature, and he found out the speed of this light wave, which came out to be 3 into 10 raised to 8 meter per second, something that is so accurate that we still use it even today. So now let's quickly outline the properties of electromagnetic waves. Now we know that an electric field is produced by a stationary charge. However, if the charge is moving, this gives rise to magnetic field. But just because the charge is moving doesn't mean that it no longer has an electric field. And therefore we say that a moving charge not only produces an electric field, but a magnetic field. That is, currents or moving charges produce both magnetic and electric field. But what about the electromagnetic wave? Who can produce an electromagnetic wave? The answer is that it cannot just be any moving charge, it has to be an accelerating charge. What does this mean? It means that if a charge is moving, but if it's moving with a constant velocity, then in that case there will be no electromagnetic wave, because when a charge is moving with constant velocity, the current will not change with time, and therefore the electric and magnetic fields will not change with time, and there will be no electromagnetic wave. And therefore this is the most important point for the production of electromagnetic waves, that is, the charge must be accelerating. That is, the charge must not be moving with a constant velocity. So we say that if the charge is moving with a non-zero acceleration, that is, it has a changing velocity, then both the magnetic and electric fields will change with time, and this will give rise to an electromagnetic wave. And so this is the first property of the electromagnetic waves, that is, they are produced by oscillating or accelerating charges. The second property is something we already know, that is, electromagnetic waves do not require any medium for propagation. And the third property says that they travel at the speed of light, which is 3 into 10 raised to 8 meter per second, given by Maxwell's equation for the speed of light, that is C is equal to 1 upon root mu naught epsilon naught. The fourth property is that in electromagnetic waves, the electric and magnetic field vectors both reach maximum and minimum values at the exact same place and the same time, because they both are reinforcing each other together, and therefore the maximum and minimum values of these waves are achieved at the same exact place and at the same exact time. The fifth property of electromagnetic waves is that the amplitude of these waves is related by the equation E naught upon B naught is equal to C. That is, the ratio of their amplitudes is nothing but the speed of light. E naught is the amplitude of electric field and B naught is the amplitude of the magnetic field. The sixth property says that the cross product E cross B always points in the direction of propagation of the wave, and therefore if you want to find out what is the direction in which the wave travels, you simply have to find what is the direction that E cross B is pointing in. At any moment in time, the electric and magnetic fields always vary sinusoidally. In fact, that's the definition of electromagnetic waves, that is the sinusoidal variation of electric and magnetic fields perpendicular to each other. And therefore, if you want to write down a mathematical equation expressing what is a electromagnetic wave, then for the electric field you'll have a separate equation, and for the magnetic field you'll have a separate equation. You have actually come across an equation just like that before in the chapter oscillation or in wave mechanics. You are basically writing down an equation for a wave which is varying sinusoidally. And as you can see, when I wrote down the equation for the electric field, E is a function of y, that is, the variation of the electric field is along the y direction, but the wave itself is moving in the x direction. Similarly, the magnetic field is along the z direction, but the wave is moving along the x direction. So here actually I have described a wave which is moving in the x direction, whose electric field is varying in the y direction and the magnetic field is varying in the z direction. So in this case, as you can see, I have written down the equation of a wave, and this is how you express at any instant of time the magnitude of the electric or magnetic field. And of course, we know, as Maxwell predicted, that light is not only an electromagnetic wave, but it is a transverse wave. That is, the direction of the electric and magnetic field vectors at any instant of time is perpendicular to each other and to the direction of the wave. And therefore, electromagnetic waves are transverse in nature, just like light waves. Now, the velocity of the electromagnetic wave depends upon the electric and magnetic properties of the medium in which these waves travel. This is obvious because when we try to find the speed of the wave, we actually have a formula in which we have mu and epsilon, both of which are the permeability and permittivity, which is their properties of the medium, and thus we can see that the speed depends on the properties of the medium in which the wave is traveling. And we also saw that the speed of the wave will reduce in a dielectric as compared to when it was in free space or vacuum. And finally, also remember that the speed of the wave is independent of the amplitude of the electric or magnetic field vectors. The next property of electromagnetic waves deals with the energy carried by these waves. It says that the electromagnetic waves carry equal amount of energy both in the electric and magnetic field. Now, previously we have written down the average electric energy density in vacuum or free space in case of a stationary electric or magnetic field. That is, UE came out to be half epsilon naught E square, where epsilon naught is the permittivity of free space and E is the static value of the electric field. And similarly, we wrote down a value for UB, which is the average magnetic energy density, that is half B square upon mu naught. So remember, you have written down these equations previously for static fields, that is, these values of E and B were not changing with time. And in this case, the total average density, that is the average electric energy density plus the average magnetic energy density, came out to be UE plus UB, which was nothing but half epsilon naught E square plus half B square upon mu naught. However, in case of an electromagnetic wave, these values of E and B are not constant with time. They are changing with time, and therefore you have to replace E and B in this equation with their RMS values or root mean square values. And therefore, if you want to write down the total average energy density U for an electromagnetic wave, you use the same equation but you replace the E and B with their RMS values, where E RMS is equal to E naught upon root 2 and B RMS is equal to B naught upon root 2, where E naught and B naught are the maximum values of the fields of electric and magnetic fields respectively. So now when we apply the property that the electromagnetic wave carries equal energy in electric and magnetic fields, it means that UE should be equal to UB, and in this case the total average energy density, which is UE plus UB, will simply be half epsilon naught E square plus half B square upon mu naught, or I can simply write it as epsilon naught E square, or I can write it as B square RMS upon mu naught. Basically, I'm using the fact that UE is equal to UB, and therefore I can write down the total average energy either totally in terms of the electric field or totally in terms of the magnetic field, because these entire terms are equal to each other. The next property says that electric vector is responsible for the optical effects and therefore is also sometimes known as the light vector. The electromagnetic waves are uncharged and are not deflected by electric or magnetic fields. Consider a wave traveling in the x direction from a point t is equal to 0 to a point t is equal to t when you are observing this wave. Now let's say that the cross-sectional area of the surface created by this wave is A, and since the wave travels with the speed of light c, the distance travelled by this wave in time t will be equal to c delta t. Once you know this, we can write down what is known as the intensity of the electromagnetic wave. The intensity of the electromagnetic wave by definition is the energy crossing per second per unit area normally around that point during the propagation of electromagnetic wave, which basically means that intensity is energy per unit area per unit time in a way that the wave should cross the area normally. So I need energy, I have to divide it by time, and I have to divide it by area. So first, to find the energy, what I'm going to do is use the formula for the average energy density which we have just found, that is UAV is the average energy density, and to find the energy I will simply multiply this by the volume. And as you can see, the volume of the cylinder will be given by C delta TA, where C delta T is just the length and A is the area of cross section. So C delta TA gives me the volume, that multiplied by the average energy density gives me the total energy of this electromagnetic wave. And what I want is the intensity. Intensity is energy per unit area per unit time, and therefore I write I is equal to U upon A delta T. Substituting the expression for U from above, I get I is equal to UAV C delta TA upon delta TA, and delta T and A gets cancelled, and this gives me that the intensity of the electromagnetic wave at any point is equal to UAV into C. That is, it is the multiplication of the average energy density of the electromagnetic wave with the speed of light c. Once you have this formula that I is equal to UAVC, you can write down what is UAV either in terms of the electric field or in terms of the magnetic field. If I write it in terms of the electric field, I get I is equal to epsilon naught E square into C, where E here I've used is the RMS value. And if I write the intensity in terms of the magnetic field, I get I is equal to B square C upon mu naught, where here I have used the RMS value of B as well. So in this way, we have found three formulae for the intensity of the electromagnetic wave at any point. The final property deals with the momentum and radiation pressure of the electromagnetic wave. Electromagnetic waves carry energy and momentum. To find the linear momentum of an electromagnetic wave, you simply divide the total energy by the speed of light, that is P is equal to U by C. This is also equal to S into A by C, where S is the Poynting vector and A is the area of cross section. Finally, remember that electromagnetic waves exert a force on any surface on which they are incident, and because of this force, we have what is known as the radiation pressure of this electromagnetic wave, because force per unit area is nothing but pressure, and therefore force exerted by an electromagnetic wave on per unit area of the surface is known as radiation pressure. So by definition, radiation pressure is force per unit area. Force itself is change in momentum upon time, and therefore I get radiation pressure is change in momentum upon time into area. And this is the formula for the radiation pressure exerted by electromagnetic waves on any surface on which they are incident. At this point, it is important to note that although Maxwell predicted the existence of electromagnetic waves in 1856, it would be many years before their existence was confirmed. Many people tried to produce electromagnetic waves but failed until Hertz came along in 1888 and proved their existence experimentally. Hertz's experiment was based on the idea that an electric charge, when it is oscillating, has some kinetic energy. And because it is oscillating, it is radiating an electromagnetic wave. And this electromagnetic wave is also carrying energy. Where is the energy of this electromagnetic wave even coming from? It is coming from the kinetic energy of the oscillating charge. Using this idea, he performed his experiment and successfully proved the existence of electromagnetic waves. While we are not going to outline the experiment here, it is important to note that studying the experiment also revealed one significant point, that electromagnetic radiation is significant only if the distance to which the charge is oscillating is comparable to the wavelength of radiation. And therefore, if you want radiation of a particular wavelength, you have to make sure that the distance to which your charge is oscillating is almost the same order as the wavelength that you require. Now, once everyone understood what Hertz was trying to say, that in order to produce electromagnetic wave of a certain wavelength, you had to oscillate the charge up to a distance almost equal to the wavelength. Once they understood this, they were able to create, that is, produce electromagnetic waves of various different wavelengths, and this gave rise to the electromagnetic spectrum. The electromagnetic spectrum is nothing but the orderly distribution of electromagnetic waves according to either their wavelength or their frequency. So when you line them up according to their wavelength or frequency, what you get is known as the electromagnetic spectrum. And you see that different parts of the electromagnetic spectrum have different properties and are useful in different ways. All the physical properties of the waves are determined by their wavelengths, and it does not depend on how you produce these waves. So these different scientists obviously produce these waves by different methods, but how they produce them did not matter. The property of the wave is only decided by its wavelength. A very small portion of the electromagnetic spectrum is something we are very well aware of. This is known as the visible light spectrum, that is the light which we see in our everyday life. This helps us see the world around us and is known as the visible light portion of the electromagnetic spectrum. As you can see, it's a very small part of a big spectrum. Another important property of the electromagnetic spectrum is that the boundary between different types of waves is not sharp. You see, the electromagnetic spectrum is made up of different types of waves, right from the radio waves, microwaves, infrared waves, visible light, UV light, gamma rays, X-rays. All of these are different types of waves. However, the boundary between these are not sharp, which means that sometimes you can create one type of wave by two different methods. Let's quickly review what are the uses and properties of the different types of waves. Right at the extreme end of the spectrum comes the radio wave. Radio waves are waves of the smallest frequency and of the highest wavelength. The wavelength of the radio waves is comparable to the size of buildings, and therefore radio waves are used in transmission. They are mainly used in radar communication and in radio and television transmission. Next up are the microwaves. Microwaves are second on the electromagnetic spectrum, right next to the radio waves. Their frequency is of course higher than the radio waves, but their wavelength is lower than that of radio waves. Microwaves have a wavelength comparable to the size of a butterfly and are used for many various purposes, most notably for cooking in a microwave oven, where the microwave basically relies on the resonation and vibration of the water molecules to cook the food. So basically, a microwave oven can successfully cook a food in which there are lots of water molecules, because these microwaves are basically acting on the water molecules inside the food. Of course, microwaves have a large number of other uses. For example, they are also used in radar communication and so on and so forth. The next type of waves are infrared waves. Infrared radiations are right next to microwaves on the electromagnetic spectrum and have a large wavelength as compared to the visible light. Now, infrared waves are radiated by almost all bodies. All bodies that have any temperature above 0 degree Kelvin emit infrared radiations, including you and me. The wavelength of infrared radiation is of the order of the size of a needle. They were discovered by William Herschel in 1800, and the story goes that he placed a thermometer at all parts of the electromagnetic spectrum, that is the visible part of the electromagnetic spectrum. So what he did was he had a thermometer with a blackened bulb, because black absorbs energy easily, and therefore he moved this blackened bulb thermometer from one part of the visible light spectrum, that is from the violet end towards the red end, and he saw that as he was going from the violet end to the red end, the temperature in the thermometer was rising. Well, that was fine so far, but he went ahead and put this thermometer in that end of the spectrum which lay even beyond the red end of the visible light spectrum. And when he did that, he saw that there was a rapid rise in temperature. And at that time, they didn't even know what lies beyond the red end of the spectrum because it was invisible. But this is how infrared radiation was discovered. They saw that there are some radiations which lie beyond the red end of the spectrum which actually give out heat. And these radiations, which we now know as infrared radiations, also came to be known as heat radiations. Now we know about infrared radiations because we actually use them many times in our daily lives. For example, when your hand or some other body part is paining, you take a hot bag of water and place it on the troubled portion. And what you're actually doing is using the infrared radiations from that hot body to relieve the muscular strain in that portion of your body. So that is one example of how we use infrared radiations. Infrared radiations are absorbed by glass but are not absorbed by rock salt and find many applications. One of the most important uses of the infrared radiation is to maintain the Earth's temperature through the greenhouse effect. What happens is that the Earth receives visible light which easily passes through the atmosphere. This visible light falls on the Earth's surface and gets reflected or re-emitted as infrared radiations, that is, radiations of longer wavelength. Now, these infrared radiations carry heat and are not allowed to go out of the atmosphere. They are trapped in the atmosphere by molecules of water vapor and carbon dioxide. And because of that, the temperature of the Earth is maintained to a temperature where it is warm enough for life to sustain. So because of the greenhouse effect and the trapping of infrared radiations, the Earth's temperature is viable for living. And in this way, infrared radiations are used to maintain the Earth's warmth. Infrared radiations also find use in many other applications. For example, the radiations that fall on the panel of a solar heater are the infrared radiations, which ultimately lead to water being heated, and thus the solar heater employs the use of infrared radiation. Similar is the case for the solar cooker. The solar cooker also employs the use of infrared radiations to cook food. Infrared radiations are also used for photography at night and also in mist or fog because they are not scattered easily and therefore can penetrate appreciably through it. The next part of the electromagnetic spectrum is the visible light spectrum. This is the portion of the electromagnetic spectrum that we can actually see with our naked eye. We use the light from the visible light spectrum to see the world around us. The visible light spectrum was discovered by Newton when he passed sunlight through a prism, and we know the very famous dispersion of white light took place into the 7 colors of the rainbow, which we call as the visible light portion of the electromagnetic spectrum. As stated earlier, it is the visible light which is emitted or reflected from objects and helps us see the world around us. It is important to note that this portion of the spectrum is visible light for humans only. There must be some other portion of the spectrum that other creatures like insects or snakes can also see. For example, snakes can also see infrared radiations and some insects can also see ultraviolet radiation. However, humans are limited by this portion of the spectrum and hence this is a visible light spectrum only in terms of humans. The next portion of the spectrum is the ultraviolet radiations. They lie on the other end of the visible light spectrum. The order of the wavelength of ultraviolet radiations is that of a molecule. The ultraviolet radiation portion of the spectrum was first discovered by J. Ritter in 1800. He observed that when silver chloride was placed at different portions of the spectrum, it was barely affected. But when this silver chloride was placed beyond the violet end of the spectrum, that is, after violet, in the portion where nobody could see anything, he saw that the silver chloride was severely affected. And therefore, he concluded that there must be some portion beyond the violet end of the visible spectrum where these rays are chemically more active than visible light, and these very chemically active rays came to be known as ultraviolet radiations or actinic rays. Thus, we can see that the radiations which lie beyond the violet end of the visible light spectrum are known for their chemical properties. However, when we looked at the portion of the spectrum which was on the red end of the visible light, That portion was known for its heating properties. Ultraviolet rays are given off by electric arcs and sparks, by some very special lamps, and by very, very hot bodies. The sun is an important source of ultraviolet radiations. However, it is important to note that the ozone layer actually protects us from the harmful UV radiations by absorbing most of it. Ultraviolet radiations is absorbed by ordinary glass, and therefore if you want to take a look at the ultraviolet spectrum, you'll actually have to use a quartz prism instead of a glass one. The next type of rays which lie on the side of ultraviolet radiations are X-rays. Now we've all heard of X-rays before, and we know of their use in medicine. The order of the wavelength of X-rays is that of an atom. X-rays are used to penetrate through human flesh, but remember they can be stopped by bones, hence they are used for detection of fracture in bones, teeth, etc. And of course for diagnostic purposes, that is to diagnose certain types of diseases and even certain types of cancer. X-rays are most commonly produced by using highly energetic cathode rays, which are stopped by a metal target made of very high melting point. Because X-rays can cause damage to living tissue, exposure to X-rays must be limited. The final type of rays on the electromagnetic spectrum are the gamma rays. These rays have the highest frequency on the electromagnetic spectrum and the lowest wavelength. The order of the wavelength of gamma rays is of a nucleus. Gamma rays are mostly obtained in emission from radioactive substances due to energy changes in the nucleus of their atoms. Gamma rays have a lot of uses, including the irradiation of food, in which they are used to kill harmful bacteria and enhance its shelf life. They are also used to kill cancer cells, that is, in the use of radiotherapy. Gamma rays are highly penetrating rays and therefore can penetrate through the human body, causing immense biological damage. In fact, they are so penetrating that they can penetrate through metallic sheets as thick as 30 centimeter thick iron, and therefore their exposure to the human body must definitely be controlled. Gamma rays are also present in cosmic radiations and are the most energetic type of electromagnetic radiations present that we know of. So this completes all the concepts that I wanted to talk about under the umbrella of electromagnetic waves. Thank you for watching. Thank you for watching this video, and if you like our channel, please subscribe by clicking on the button below, and if you'd like to get your very own target book, you can click on the button here. Thank you for watching and stay tuned for more updates.